So I wanted to do an example or two of the types of problems that we might have run into in Chapter 13. And the first one I thought that I would look at would be a problem dealing with a banked curve. One of the reasons that I think that this is a good problem to do is that even though when we look at the banked curve, it kind of evokes the idea of an inclined plane, we do treat our axes different. Our coordinate axes that we use when we do the banked curve. Part of the reason for that is we actually are really thinking about the fact as the curve is banked because it's a curve, you're going around in sort of a circular-like pattern, and because of that you have a centripetal acceleration. And so that centripetal acceleration is directly in towards the center of your circular path or your approximate circular path. And so we want to arrange our coordinate axes so they correspond so that you actually have an axis along that direction, which if you think about normal and tangential coordinates, it would be along the normal coordinate, and we would be talking about v squared over rho as our normal acceleration. So what I'm going to do is I'm going to first of all just draw the axes that we're going to use in this problem. Now, this is in the normal direction, so I'm going to just write that this is the unit vector in the normal direction. Now, the way that I drew this, I don't know if it's obvious, but to see the banked curve and the car on the banked curve like this, the car is either like coming at us out of the screen or going into the screen. And so for that reason, I'm going to say that the tangential direction, I'm going to say is like this, and so this direction is tangential, and then this actually is in that B direction. Oh, that didn't fit on my screen, so let me move that down. So I kind of told you that we'd never use that B direction that was in our notes and in the book, which is basically the third unit vector to make a complete three-dimensional unit vector set when we use normal and tangential components. But the tangential really should be along the direction of the motion because that's what it really means. And so this vertical axis is that B direction. So I lied, whatever. I lied. So now the question that we're actually answering is, if there is friction between the tires and the banked curve, what would be the safest, fastest, the fastest safe speed that the car can go and not have any slipping? If you think about when you go around the curve, you tend to feel like you're pushed outward. So the impending motion for this car would be up the banked curve, which would mean that the frictional force is going to be tangent to the curve itself. Other forces that we're going to have are going to be the weight, mg, and then the normal force. And actually, I think that's it. So the thing that I forgot to mention was the mass of the car. Actually, I didn't mention it because we're not given it, and we'll see how it cancels out. And we can see that we're going to use foot, pounds, and seconds for our units because our rho is in feet. And just to sort of clarify, so this angle here is going to be the 30-degree angle, and then the weight is, of course, along that direction, and the angle between, so this angle here is 30, so this angle right here is 60. That's the angle that the friction is making with the B axis. So just so we're clear on that. Hopefully you can see all that. So what I'm going to be doing is I'm going to be using the forces in the B direction, which are going to add up to be 0 because I don't expect this car if we don't get any slippage, is not going to move in this vertical direction. And my forces in my normal direction are going to be equal to mv squared over rho. So again, I've opted to look at this from the viewpoint of normal and tangential unit vectors because of the fact that I'm talking about sort of circular motion, and I know I'm going to have the centripetal acceleration. It just pairs well with this problem. And I also use that third unit vector b because it just works out well with the situation that we have right here. Now, what are the forces that have components in the direction of u sub b? Well, I have all three of my forces actually do have some sort of component in that direction. First I have the normal force has a vertical component and it's positive. The weight is exactly downward, and so that's just minus mg. And then the friction is minus f times the cosine of 60, and that's just sort of the geometry that's going on there. So at first this seems like this is kind of difficult, but you know what, let's look at the normal forces as well. In the normal direction, I have n sine 30, and also the frictional force times the sine of 60, and those are both inward, and so they're going to be equal to mv squared over rho. Now, one of the things that I remember is that the frictional force is related to the normal force. And you know, the frictional static force is less than or equal to mu s times normal. And if we want to do the fastest speed, then we need the biggest friction. So we're going to say that our static friction is equal to mu s times normal. And this is going to allow us to figure out what the normal force is because it's equal to 0 and we can write friction in terms of the normal force. I'm going to be able to solve for normal through some rearranging. So let me show you what I mean. So I get this expression for the normal force in terms of other quantities that I know, and I'm going to be able to substitute them in here. First I want to write what the normal, how friction is related to the normal here. And so this is going to be one big old mess, but both of these terms, because they both have normal, are going to have the same denominator. So I'm just going to put it all together. The denominator that we had was cosine of 30 minus mu s cosine of 60. And here I have mg times the sine of 30. And then here I have plus mu mg sine of 60. And this is equal to m v squared over rho. Now, this is where we come to the point where we realize we didn't need to know the mass of the car. And so this is why sometimes I tell you not to worry too much about, you know, if you feel like I should have been given this value, but I wasn't, and now I'm all like, how can I figure it out? It's okay So it turned out okay. We just had to sort of soldier through and figure it out. You can see that if I multiply through by row to both sides, and then I take the square root, I can solve for v. And so because it's a lot of writing, I'm not going to go through that stage, but I think it's pretty clear how we can use this expression now. Everything I have is a known quantity. I can plug in, solve for v, and I get 119 feet per second. So that's the fastest that car can travel and not slide. An interesting problem to do is then to also find a minimum speed, because if you go too slow, you'll tend to slide down the incline. So we would do exactly the same problem, but our frictional force would be pointed the other way, which is going to have an impact on all of our equations, and is going to give you a different value for velocity. And so if you're bored, maybe you should try that.